In the previous segment, we solved the Schrödinger equation for an infinite potential well without even writing down the Schrödinger equation itself. So of course, it doesn't always happen this way. So for more complicated potentials, we actually have to do some calculations. And in this segment, I'm going to present an example of a general method actually that is used to solve the Schrödinger equation. And I will consider a so-called finite potential well. So the potential that we're actually going to study is illustrated here. So here's a formal sort of mathematical expression for this potential, and this is the it's an illustration. So for x, so this is one-dimensional potential. For x greater than a over 2 or smaller than minus a over 2, we have a finite wall, if you want, with a height of u naught, and in between minus a over 2 and a over 2, we have a potential well. And so the question that we're going to be interested in is whether or not we have levels, energy levels, allowed states within the potential well, which implies that the energy of these states must be smaller than this maximum u naught, but larger than 0. So these are positive energies here in this formulation. Now, clearly we have three regions that appear in this potential. So one region will be to the left of the point minus a over 2. The second region, which is the potential well itself, will be between minus a over 2 and a over 2. And the third region is x greater than a over 2. And for each of the regions, we can write down the corresponding Schrödinger equation. Let's say for the regions 1 and 3, for absolute value of x greater than a over 2, we have the kinetic energy plus the potential energy u naught is equal to the energy that we're actually looking for, E times psi of x. And for the region of the potential well, we formally have just the free Schrödinger equation, since the potential here is equal to 0. Now, to solve this Schrödinger equation, the main challenge in some sense of solving the Schrödinger equation would be to match the solutions in different regions. And by match, I mean the following. We're going to demand that both the wave function itself and its first derivative are continuous everywhere. In particular, in these matching points, minus a over 2 and a over 2. And so here I formally represent it as so. So plus 0 basically means to the right of a certain point, and minus 0 means to the left of a certain point. And the reason we want our wave function, or let's say its derivative, to be continuous is because if we do not have this continuity, let's say in this point, if we, let's say, solve our Schrödinger equation in region 3 and in region 2 independently and don't bother to match them, then in general, so our wave function in this case is going to be something like this, let's say, and there will be a jump, a finite jump in the wave function or in its derivative. And if we calculate the second derivative here, due to the jump, we're going to have an infinite second derivative, which wouldn't be able to compensate in our Schrödinger equation. So there will be essentially a delta function coming up from this discontinuity, and well, we don't have it in our problem. In our problem, we don't have a delta function. So therefore, we must demand that the wave function and its derivatives are continuous everywhere. And it turns out that this, along with this condition, would be enough to find the constraints which will determine the actual energy level. So now the latter constraint, namely that the wave function should decay at infinity, is essentially a physically meaningful constraint. So we are looking for a bound state of our particle. So we want the probability of finding this particle at infinity to be 0. And we want the probability to be sort of localized in the vicinity of the potential well. And so this is where the second constraint is coming from. Now, to simplify this equation a little bit, we could just notice that, well, we can rewrite it. Let's say the first one, we can introduce a new parameter gamma, which is 2m over h squared u naught minus epsilon minus energy E. So let me actually call it gamma squared. Well, we can just put the energy in the left hand side and multiply everything by minus 2m over h squared. and this would give rise to the following equation: psi 2 primes minus gamma psi is equal gamma squared psi is equal to 0. So and for the second equation, we can introduce the parameter, let's say k, and we are going to have this with psi 2 primes plus k squared psi equals to 0. So let me just rewrite it in a slightly nicer way. So here are basically the two equations I just wrote, and here are the parameters. Both these equations are actually very simple equations. So this one has solutions e to the power plus minus gamma x. You can just plug it in and see the derivative of the exponential, and the exponential is the exponential itself, and well, clearly it's going to satisfy this equation. And the second equation, well, which is the free Schrödinger equation, unsurprisingly gives us just plane waves as the solution, e to the power plus minus I k times x. So, and again, the challenge is going to be to match those guys in each of these points, minus a over 2 and a over 2. Now, it's not really necessary for the solution of the problem, but I would like to use the symmetry of the problem here, and this would give me an excuse in some sense to introduce the symmetry concepts in quantum mechanics in a much broader context. So, namely, I would like to point out the following fact. If the Hamiltonian commutes with an operator A, this can be an operator of any physical quantity, then the solutions to the Schrödinger equation, that is an equation which is an eigenvalue problem for the Hamiltonian, so then these solutions can also be chosen to have definite value of A, which means that the same solutions are going to be the eigenstates of the eigenvalue problem for this operator A, whatever it is. So in general, if the two operators were not to commute, so I wouldn't necessarily have been able to find such a set of wave function which would have both A and E, the energy, definite. So, but in the presence of such a symmetry, if you want, this possibility exists. Now, what does it have to do with our problem? So in our problem, we have a sort of rather obvious symmetry, which is essentially inversion symmetry of the potential. So if we flip x, if x goes to minus x, so the potential is unchanged. And so the kinetic energy also doesn't change, so since it's a second derivative with respect to x, so therefore the Hamiltonian, one can check that the Hamiltonian is indeed symmetric or invariant under this operation. And so the operator that actually enforces this inversion is this operator I, which basically takes x to minus x. And this operator has two eigenvalues, the parities, which are either plus or minus 1. So the functions which are eigenfunctions of this inversion operator are either even or odd function of the coordinate. And so what we're saying in this sort of very complicated language is that we can find the eigenstates of our problem, the solutions to the Schrödinger equation, which would be either odd or even functions. That's all we're saying. And well, another statement I would like to make is that if there is a symmetry in the problem, you better use it. So it always simplifies things. It never makes things more complicated. It always simplifies things. And so that's what I'm going to do here as well. So in general, if I were to ignore the symmetry, so the solution to the Schrödinger equations we just discussed in this region of the well would be an arbitrary linear combination of two plane waves. Now I'm saying, so since there is this symmetry in the problem, so I would like, instead of just having this arbitrary coefficients C1 and C2, I would like to consider separately solutions with definite parity, either even functions, which is basically cosine with C1 equals to C2, or a sine, which is an odd function, in which case C1 is equal to complex conjugate, and these are purely imaginary constants. So in the following, I'm going to specifically focus on this even solution just for simplicity, but you can find the general analysis in a number of books. So this is the problem we're solving, by the way, is an absolutely classical problem. Well, classical not in the sense of classical physics, but in the sense that it appears in just about every course or every book on quantum physics. Now, having determined the solution we're interested in region 2, we now have to determine the solutions in regions 1 and 3 that we're going to be focusing on. And by the way, due to the symmetry of the problem, we can actually pick just one of these regions. So we don't really have to use, in this case, both matching points. We can do, well, just using one point. And as we discussed, the general solution to the Schrödinger equation, to this equation in the region 3, is given by a linear combination of these two exponentials, which are no longer oscillating functions, but are functions that are either rapidly decaying function or a rapidly growing function. And so to simplify, to find the appropriate solution in the region 3, let's say for x greater than a over 2, we have to recall the constraint at infinity, namely that the wave function must remain finite. Well, actually I should correct it. It should actually go to 0 as we go to infinity. So otherwise, if we don't impose this constraint, if we allow, in this case, this term in the wave function, the probability for particle to leak in some sense to infinity would explode exponentially, which doesn't make any sense. So therefore, we simply drop the b term in this wave function and only will focus on the on this wave function in the region 3. So now we're in a position to actually match the solutions. We know the solution in each region. So here I do present a solution in all of the regions, including region 1. So this guy is for region 1, this guy is for region 2, and this guy is for region 3. But as I said, due to the symmetry, we can focus only on one matching point, and this is what I'm going to do. So now we can write the wave function to the left at this point, which is going to be c times cosine ka over 2. And it must be equal to the wave function to the right, which is this guy, which is e to the power minus gamma a over 2. So this is the first matching condition. And the second matching condition is going to be the derivative of this function. So the derivative of cosine is minus sine. So we're going to have minus c times k sine of k a over 2 to the left must be equal to minus a gamma e to the power minus gamma a over 2 to the right. And now what I'm going to do, I'm going to divide, so let me call this equation equation number 2, and this is going to be equation number 1. And so if we divide equation number 2 by equation number 1, which we're allowed to do, what we're going to get in the left hand side, we're going to have k times sine over cosine is the tangent of ka over 2. And in the right hand side, so the minuses will go away and the exponentials are going to go away. We're going to get just gamma. So here I have the same equation written explicitly in a nicer way, and also I recall the definitions of gamma and k that I made in the previous slide. So k itself is the square root of 2me over h squared. And the energy is really what we're looking for. And energy appears both in the left hand side and in the right hand side in a rather nonlinear way. And as a matter of fact, there is no way we cannot solve this equation analytically. So this is a nonlinear algebraic equation, and it doesn't have a formal sort of closed solution in nice form. So which, by the way, is quite amazing that the problem as simple as this finite potential well in one-dimensional quantum mechanics, which is just about the simplest problem you can think of, cannot really be solved. So this gives you something, tells you something about the complexity, of the technical complexity of the Schrödinger equation. Now, to proceed further towards a bit of numerical analysis or asymptotic analysis, it's always a good idea in such cases is to get rid of the dimensional quantities such as energy or this potential height, which have physical dimension, and go to dimensionless parameters. And so here, the natural dimensionless parameters are going to be, well, basically the argument of this tangent, which is ka over 2. And the parameter introduced here, so which is basically to be able to write our equation in a nice and dimensionless way. The reason why dealing with dimensionless quantities is much more convenient than with quantities that has non-trivial physical dimensions is because for the former we can talk about them being large or small. So we can say that something is small or large, just comparing it with 1. While for a dimensional quantity, it doesn't really make sense to talk about large or small unless we specify what we actually mean by that. For instance, is 1 meter large or small? well, it doesn't. We don't know unless you compare it with the, let's say, size of an atom, in which case it's clearly large, or with the size of the universe, in which case 1 meter is really small. So here, once we get this parameter psi, it allows us to define basically a deep and shallow potential. So we will call the potential deep if this guy, if this psi squared is going to be is much larger than 1, and the potential is going to be called shallow if it's much smaller than 1. And by the way, in the following 2 video segments, we're going to be focusing on shallow potentials, which are well modeled by a delta function. So naively you would think that delta function is something which is actually very deep, because it goes to infinity if you approach x equals 0. Let's say if we're talking about potential u of x, which is, let's say, minus u delta of x. But delta of x, a potential delta of x, is really a means to represent a potential with a very small radius. And the radius, in order for the integral of the delta function to be equal to 1, so the radius of the potential, the size of the potential, should scale with the depth of the potential as so. So as a goes to 0, u naught is sort of proportional to 1 over a. But here we see that the definition of a shallow potential is u naught a squared times m over h squared must be much more than 1, which means that the delta potential is actually closer to a shallow potential, which is an important observation that we will take advantage later on. But at this stage, let me just say that, well, we have these 2 special cases, and we can, even though we cannot solve exactly this equation for arbitrary psi, we can do 2 separate analyses of this equation in such 2 special cases. And here I present this analysis. So this is again the equation, the same equation. So the red tangent of x is plotted here. So here basically I plot the functions on the left of this equation and on the right of this equation. And you see, by the way, that when x becomes larger than psi, so this right-hand side becomes purely imaginary constant, which implies that there is definitely no solution to this equation, as the tangent here does not become imaginary. So it makes sense only to plot this function for x is smaller than psi. So here I have an example of a deep potential where I say set psi 220. And so I have all these red curves corresponding to the tangent, and this blue curve corresponds to the right-hand side. And wherever I see a crossing between these 2 guys, so let's see here, 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 etc. So I have levels. So in this case, I can count the number of levels that are allowed in this quantum. Well, 1, 2, 3, 4, 5, 6, 7 levels are allowed, well, for the symmetric wave functions, if psi is equal to 20. Now let's consider a relatively shallow potential on the other hand. So let's say with psi equals 1. In this case, I only have to plot these functions for x smaller than 1, and there is just one crossing between the blue curve and the red curve, which means that there is just one single level in the shallow potential well. Which, by the way, is a very important result that we're going to confirm on the case of a one-dimensional delta potential. And we're going to see how this result is modified in higher dimensions. Now, the last comment I'm going to make is that in principle I could have continued this analysis of this self-consistency equation, and there is a lot to do to determine the actual numerical value of the energy levels, to see what happens with the antisymmetric levels, with the odd wave functions. And I'm not going to do it right now in the lecture because admittedly it's probably not the most exciting thing in quantum mechanics. So I will, however, encourage you to take a look at various textbooks and other lectures online. For example, this set of lectures by Professor Michael Fowler at University of Virginia. And also you will see a few problems following up on this solution in your homework. So you will have a chance to look into this problem in more detail and understand the solution at a deeper level.